Ever wonder how AI models like ChatGPT or GPT-4 get better at answering questions? It's not just about feeding them more data, it's about teaching them what to learn. Today, we're diving into a breakthrough in AI training that solves a tricky problem: why some models get stuck in a loop of repeating the same answers. Let's break it down. So here's the issue. When AI models like chatbots are trained using a method called self-rewarding, they try to improve by comparing their own responses. But here's the catch. Over time, their chosen and rejected answers start looking too similar. Think of it like a student who keeps writing the same essay. Sure, it's polished, but it's not learning anything new. This is where the math comes in. Researchers found that when the differences between these responses shrink, something called the DPO gradient, which guides the model's learning, starts to vanish. It's like a car's engine losing power. Without that push, the model can't keep improving. But here's the twist. Our team discovered a clever way to keep that engine running. Instead of letting the model compare just its own answers, we use two phases to keep things fresh. First, we anchor the model to its past capabilities, like checking an old draft to spot mistakes. Then we let it peek at a future version of itself, using smarter responses to guide improvements. It's like having a mentor, the past, and a visionary, the future, work together. The result? A stable training process that avoids the repetition trap. While other methods might take 4 rounds to tweak answers, our approach does it in just 2, and with better results. Imagine a student who not only revises their work, but also gets feedback from both their earlier self and a more experienced version of themselves. In tests with models like LLaMA and Qwen, this method outperformed traditional approaches. The key: keeping the gap between good and bad responses clear, so the model always knows what to aim for. But let's dig deeper. At the heart of this is something called self-rewarding models. Think of it like a student who grades their own homework. Instead of relying on a teacher, the model evaluates its own responses and adjusts to do better. But here's the twist. The old way of doing this has a big blind spot. Here's the problem. Standard self-rewarding methods compare 2 responses, a good one ew and a bad one ill. The model learns by looking at the difference between them. But imagine this. As the model gets better, those bad responses start sounding too similar to the good ones. It's like grading a test where every answer is almost right. There's no clear signal to guide improvement. The math behind this is where things get tricky. The model's learning signal, its gradient, has 2 parts, a weighting term and a direction term. The weighting term acts like a volume knob. When the model is unsure, it turns up the volume, giving a strong nudge to learn. But when it's confident, the knob turns down, reducing the update. The direction term tells the model to favor the good response and avoid the bad one. But here's the catch. If the good and bad responses are semantically similar, like paraphrases, their gradients start to cancel each other out. It's like trying to steer a car with both the gas and brake pedals pressed. No progress. This is why standard methods hit a plateau. Enter temporal self-rewarding, the game changer. Instead of using the same model to generate both good and bad responses, this method splits the task. The bad response ill comes from an older, weaker model, while the good response ew is generated by a future, stronger version of the same model. It's like a student learning from their past mistakes while aiming for their future potential. The results? Stunning. In experiments, models using temporal self-rewarding outperformed traditional methods across metrics like AlpacaEval and MT-Bench. For example, a mid-sized model, LLaMA 3, saw a 20% improvement in task accuracy, while larger models like LLaMA 70 showed even bigger gains. The key: by comparing against a future version of itself, the model gets clearer, more actionable feedback. No more fuzzy, almost right answers. So what's the takeaway? AI isn't just about raw power, it's about smart, structured learning. By decoupling past and future insights, we're paving the way for models that adapt, improve, and actually get better over time. Thanks for watching, stay curious, and let's keep exploring the future of AI together.